All right, it's just about 2:05, so I think we've got some people still trickling in, but we will go ahead and get started. Today we're going to be talking about using a message broker with DQMH actors, and the application in particular is a high-speed, high-throughput data logger, and it can also be used for playback, which we're going to get into a lot of those details later. If you haven't met me yet, my name is Becky Linton. I'm a senior systems engineer / manager for Conrad Technologies in the United States. I'm a LabVIEW champion and a LabVIEW architect. I've been using LabVIEW for over 20 years now, which makes me feel really, really old. And then I'll go ahead and let Chris introduce himself.
Thanks, Becky. Yeah, so I'm Chris Roebuck. I'm a LabVIEW architect at Conrad Technologies based out in the UK. I've been using LabVIEW for a long time because I actually am old.
Oh, come on. I guess we're all getting to that point now, I feel like.
Yeah.
All right. Before we even get started, we wanted to put a big thank you out there for the LabVIEW community. We're all sad that VIWeek did not get to happen this year. This is actually the presentation that Chris and I were going to give and that was accepted. But everyone worked together, and I was amazed that in 2 weeks we had this up and running, and now there's the awesome Discord channel and different things going on. And I'm really happy to see where the LabVIEW community is going to grow, especially how it coincides with the release of the community edition. We also wanted to put a big thank you out there to the Conrad Data Logger development team. A lot of the stuff that we're talking about today, some of it I didn't code, Chris didn't code, but a lot of it is from this team. There's a global team of development, and there's hours that have gone into this project. But in our opinion, I think it's pretty cool what we're going to be sharing with you guys. Before we get too far, I wanted to point out what we're going to talk about. There are some major prerequisites or ideas that you should at least have a small idea about before we get too far. So I'm going to talk about those. And I'll introduce the idea of a message broker and talk a little bit more about the project background. And then I'll turn it over to Chris for some demos and the actual software architecture we came up with that uses a message broker, and then how the messages work behind the scenes in our software. So some prereqs to start. Object-oriented programming, actor model, DQMH, DVR, eDVR, malleable VIs, and maps. So there's a lot of big things going on in there, but we were actually excited to use all of these in our project. One thing I want to point out is almost every one of these topics could be an hour-long presentation in and of itself, if not longer. So to conserve time, if you have any questions regarding any of the information I'm going to cover before we get to the message broker, please post it over in the Discord, and we will open discussion for those after the presentation. And there's a link to Discord in the meeting Q&A. You should see it as an announcement. First off, object-oriented programming. If you're like me, you're an electrical engineer, kind of a fun side note, I actually switched from computer engineering to electrical engineering because electromagnetic fields sounded like more fun to me than Java 2, because I just was not getting the computer science stuff when I was in college. And so one of the things that actually really turned my head around how OO works and stuff was the computer science for the G programmer. And this was an VIWeek presentation by Stephen and John a few years ago. If you haven't seen those, they're excellent. But the two things that we really, I guess, took, advantage of in our whole application is abstraction and inheritance. And so I have a simple object-oriented statement here around musical instruments that I'm going to hopefully explain things in a way that'll make sense why we did what we did. So let's pretend we have a class called instrument. And in that, we have two children. We have a piano and we have a trombone. Not too bad. That's showing the inheritance. We have a parent class, instrument, and two children. Now, the parent class has methods that can play various notes. If we take a look at one of the methods of the instrument class and the parent, there is actually no code implemented. The intent here is that the behavior is implemented in the children. So generally speaking, this instrument is an abstract class. We're not really doing much with it. So here's the children, and here's what their overrides look like. So they play the note on the specified instrument. So why are we bothering to have this abstract parent? The child's just doing the work. Let's just have individual music ones. Well, the key comes down to we have a higher level application that plays notes. If we use the abstract parent method at runtime, we can either call the piano or the trombone class. Seems simple, but it allows us to extend it so that we can play any song on any instrument through the note methods. So hopefully that makes sense. The general idea of having an abstract class that you call at a higher level, and then at runtime, you can inject the behavior of the children. The actor model of computation. If you have never seen a Dimitri presentation, please go. I have some links that we're going to be sharing shortly, and he's got some great presentations on the actor model, and there's some others out there. But the key here is an actor is a universal primitive, and it talks to the world through messages. It's meant there to do its own thing, but it can talk to other actors. It has a small job that it's supposed to do, and it tries to stick to that job. There's a bunch of other presentations on this, like I said. And one thing I want to point out is people often hear actor-oriented design or actors, and they think it's actor framework immediately in LabVIEW. That's not necessarily true. It's actually more than that. And so here's what a software architect needs to know using actor framework. That does involve it. There's some fundamentals of actor-oriented programming, and then solid actor programming, which doesn't use the actor framework at all. So these are great links, and Chris is going to be sharing them, I hope, in the announcements. Next is DQMH. That's the Delacorte queued message handler. A lot of you have probably used this before. It's an expansion of the NI queued message handler template, and it provides the event-based message handling. It has a lot of scripting tools and awesome documentation, including some videos showing you how to get started. We actually utilize DQMH and actor framework, and I'll talk about how we had a split in the middle there in this project. And one of the things we went to is DQMH actors. And if you're interested in the idea or how it works with self-messaging and helper loops, there's a guest blog on the Delacorte website by Jorg. And so I would recommend going and reading that in detail. What we did is I want to talk briefly about our KT DQMH actor module template. We made some changes to the request and wait on broadcast. What we wanted to do was still allow for a timeout, but also check for, was there an error? Was somebody requested to stop? Did some major meltdown happen somewhere else in the code? It just allowed us to extend the behavior of the DQMH template. A few other things we often do is we actually replace the class. Usually this is a cluster in a DQMH module, but we replaced it with module private data. And that means that every case we try to make in our model handling loop is a method. And this will separate our code from the DQMH framework to kind of say that's DQMH stuff, this is Conrad stuff that we've changed. Something else we did that's interesting is we actually overrode the module message queue that comes with DQMH so that we could plug in our own error handling behaviors. And one other thing we did to kind of make this more of an actor or identifiable to our other engineers is we have a private API folder, and that's where the actor can put its events that it wants to call on itself. So it can tell itself what to do. And Chris mentioned this, and we made this kind of a developer rule across the line with all of our classes, is we actually chose not to use property nodes for accessors. And the reason why is if you use the VI and constantly use it throughout the program, you can find all instances and see where it's at, where it's being called, in case you're wondering, why is this getting overwritten? It shouldn't be overwritten now. You could search for the right, data and then go find where it's at. Next is the DVR and the eDVR. So DVR stands for data value reference, and it looks like this in LabVIEW. Here we're creating one with some data in it. There's the wire. It can help with the memory management and avoid data copies, but you have to be careful when you use it to avoid race conditions. The eDVR is very similar, and this became very important for our high throughput streaming. But basically what's happening is it's called zero copy by NI, but we're going directly within the driver DMA buffer from the hardware to the disk without actually hitting LabVIEW memory. So that allows us to either use DVRs or eDVRs to pass around our data. And believe me, we have a lot of data. We're saving, I think at one point, we had close to 5 gigabytes per second to disk, which is a lot of data. Malleable VIs, these are VIMs. These were introduced in LabVIEW 2017. They're very similar to polymorphic VIs, but they don't have a predefined list of acceptable data types. Chris is actually going to show you ours later on because there's some fun stuff that happens when you try to build one of these on your own. But I put a couple screenshots on here of common ones that NI has now included on the palettes. And so one is stall data flow, and it lets you put that in on any wire. So it doesn't care if you're stalling data flow on a class, on an error, on whatever you want. You don't have to do something weird to just put a little bit wait statement in there. And then there's some of the common ones, like there's a bunch of them on the array palette for removing duplicates and sorting and so forth. And maps, finally, before we get out of prereqs. These were introduced last year. So this entire project is actually built in LabVIEW 2019. I know some people tend to stay a year behind, just watching out for patches or whatnot, but there were too many new features in 2019 that we wanted to take advantage of that we actually have the entire project in 64-bit LabVIEW 2019. And we're actually using maps. And so a map realistically groups key value pairs together. It's like a lookup table. And the keys and values can be any LabVIEW data type. And there's a picture over here. This is directly from LabVIEW Help. It's showing that these are our keys. In this case, it's a string, but it could be a number if you wanted it to be. And then over here, our value is a number, but it could be a variant. It could be a class. It could be whatever you want it to be. And then this is telling us our size. And the entry is kind of the combination of the two together. And notice that the wire color will actually change based on the data type color. So if this was a string, this would be a pink map. It would show up a little bit different. So let's take a look at what a message broker is. Chris, are there any questions so far? I mean, hopefully most of them will be over at Discord, but.
Just the point from Norm that apparently we can now find all instances of property nodes. So that's good news.
I actually tried that in LabVIEW 2020 today and it didn't work. So I'm curious. But it was the community edition, so maybe I did something weird. Maybe I'm looking in the wrong spot.
Yeah.
So we'll have to take that offline. But nonetheless, what is a message? So whenever I'm trying to explain something to someone, I often go to the dictionary or Google, right? And so one of the common, at least in the US, dictionaries is Merriam-Webster. And so when I said, okay, what's a message? They actually came back with a communication in writing, speech, or by signals. And that's kind of an okay definition for message. It makes sense. But I actually liked what I found on Wikipedia a little bit better for a few reasons. They talk about it as a discrete unit of communication, and it's meant for consumption by a recipient or group of recipients. And the message may be delivered by various means. And I kind of laugh, but they have courier, telegraphy, I can't even pronounce that word, carrier pigeon, electronic bus, doesn't matter, it can get around somehow. And I like this because it maps to what I'm going to be talking about in a few minutes. So if we look at the simplest message on LabVIEW, it's a wire. We have a source, which is our input here, and then we have an output, and the wire is kind of our layer of getting it there. So we're sending a message. We're taking an input, putting it straight through. So if we break that down a little bit more and look at a few other LabVIEW data types, you have different types. These are controls, could be constants, but this is some kind of type, something we want to package up and send to somebody else. Could be a cluster, could be an array. Then we have a transport, which is a method or some sort of way to get it from point A to point B. And then finally, we have the address or our destination where we want the message to go. So I have a quick example here, just fun. I like to usually throw my family in some of my presentations. But my dogs, Jack and Mars here, they've been pretty good all quarantined. They've been putting up with us humans. We're home all the time. I think the kids are really starting to annoy them at this point. They want the dogs in every Zoom meeting, but it's all good. But because of that, I think they've taken some of their frustration out on their toys. So we decided we're going to buy them a new toy. And when I order that toy, it just magically appears at my house. Had I ordered it from Amazon, at least in the US, this comes to me via the Postal Service or UPS. If I ordered it from Chewy, another dog supply company, it comes FedEx. As a consumer, I really don't care where this comes from, as long as it gets to my house. So if we take this back a little bit, what's our type and so forth? So the type is the package, or it's what I want to give to someone else. The transport, again, is how it gets there, and the address is where I want it to go. Let's step back out of my really simple example and go back to LabVIEW. If you actually look at the producer-consumer design pattern, there is some messaging in there. It's not too bad. Hopefully people can pick it up because it's a little bit obvious in the name. Here it is here, the message name and message data. So it's this left-hand side of my producer-consumer. So let's look at the cluster elements and the queue. If we break this down, the type is whatever we're putting into the message data. It's the variant that's there. The address is the message name. It's like who's going to get it. So who's going to subscribe to this? So this is a named queue. And the transport layer itself is actually the queue wire. And if we imagine that producer consumer is a single actor, a single piece of code that operates and does its own job, that's great. But now that actor wants to start talking to other people. Here we're going to use airplanes to kind of represent these actors. If we ramp things up and we're at 3 planes, this isn't too bad. These 3 planes need to know where the other planes are so they don't crash and there's nothing happening. And they know what's going on. What packages do you have? Where are you going? Oh, do I need to transfer this package to you? That's great, right? But things can get busy really fast. So even if we just jump up to 7 planes, there's a lot more chances of collisions. So as actor-oriented systems grow in size, they can grow in complexity. So the messaging schemes start to couple the actors together. And it basically comes to the fact that they all need to know who to interact with and who's there and what's going on and when do I send my stuff. Well, if we put in an air traffic controller, we can have a mediator. That's what we need, someone to keep track of all the available destinations and locations so we don't have collisions. And that's kind of the purpose of this guy. So I would send a message to the mediator, the air traffic controller, and he forwards it on to someone else. This is actually a software design pattern. It's called the mediator pattern, and it maps well to this analogy. So the air traffic control tower mediating the communication between airplanes is the same as if we're talking about a message broker mediating the communications between modules or actors. Here's another way to look at it. So the mediator pattern is a design pattern that promotes loose coupling of objects by removing the need for classes to communicate with each other directly. And this snapshot here was actually taken from one of Dimitri's presentations. And I mentioned this earlier, but if you've never seen one of his presentations, they're great. Dimitri is a super sharp computer science guy, but he can take some of these super complex topics and break it down in graphics and things like this to help other people understand who might not have a PhD in computer science. Now, what we ended up using actually at Conrad is something that John McBee released. It's called Stream, and it's basically the mediator pattern for LabVIEW. It's found on the LabVIEW Craftsman blog, and if you've never read that, please go there. Some of the pictures and stuff I've actually just shown and the information with the airplanes and the air traffic controller, that all came from John on the Craftsman blog. He gave us permission to use that and so forth. And so I wanted to make sure that that's a link, and you guys go visit that if you haven't before. He has the code up there for free. You can extend it, which is what we did at Conrad, and Chris will talk about our extensions. They've since at Composed Systems moved a little bit away from Stream, and they've moved to something called the MVA framework, so I wanted to be sure to mention that. We did not use this. We're not familiar with it yet, but this is what John uses, and it's an extension of the LabVIEW actor framework. So Stream, you don't necessarily need to use the actor framework. It's a message mediator without it, whereas the MVA framework is an extension, and that also has its own Git repo where you can contribute and also use.
Okay, thanks, Becky. So, oh, you might need to go on mute, Becky. Okay, thanks. So in this video, we're going to take a look at the basic principles of a mediator on a single block diagram. So let's take a look at that. So I think we might need to reset that, Becky, if that's okay. Cool, thank you. Okay, so on the in the blue highlighted decoration, we've got our mediator. That's our message broker, if you will. And then we've got several loops. The top loop marked as source, that's not our mediator. That's goofy, I guess. Probably more fun.
I was trying to make sure there was questions over in Teams. I'm good.
Okay, so our top loop, we've got our data source. So our data source is basically registering itself as a publisher to the message broker and obtaining a message transport. We've then got for loops, which are our consumers, our data sinks, our recipients of that data that's being published by the source loop. Each one of those loops could be considered, it could be easily replicated in an actor. So we've basically got one publisher and 4 consumers. Notice also that each of the consumers has dictated how it wants to receive the data. So the data is being published in the top loop via queue. But each of the consumers is basically providing a message transport to say, hey, here's how I want to receive the data. So in the case of the top 2 sinks, as we call them, we are basically saying, I want to receive the data as a user event. So the source is publishing a double precision value, and each of the 2 sinks is receiving that as a user event. Lower down, the bottom 2 sinks, they've chosen to receive the data on a queue. And then periodically they're flushing the queue and pulling the data off that queue. So in the example that we've got on the left, we simply update the control for the data being published, and we see that all of our recipients receive that data at the same time. Thanks, Becky.
All right, we'll go back. So let's take a little look at this project background. So this is a large project that spanned many years here. Back in August 2018, Conrad US kicked off a project for a data logger. So the whole key to the data logger was a customer wanted a high-speed, high-throughput, synchronized data logger. It wasn't just your typical DAC and CAN, but we had the SIRDES cameras or MIPI CSI2 cameras in there. And that's how the Conrad got involved initially, was from our particular piece of hardware. It's custom hardware we have that does this. And they wanted it to be synchronized to the rest of their system. And so we decided to use the actor framework and to develop actors that were related to the bus type. There would be a CAN actor to record the CAN data, a SIRDES actor to record the image data, and the alpha release logged the data directly to disk when the software was started. There wasn't really any control. If the software starts, it logged it to disk. When we got to the beta release, we had a ring buffer and minimal control to start, stop, and trigger different sessions. In early 2019, we had some other requests from customers saying, hey, what you guys are doing sounds awesome, and we also want it to play back the data, not just record it. So we had coupling right there within our actor that we were saving to a certain file type and getting it from a certain interface from a certain part of hardware. And so at VIWeek in 2019, we met with a bunch of R&D people and discussed opportunities and then compatibility with any future NI platforms in case NI was working on something else. We wanted to make sure anything we did now would move forward. And so that leads us to what happened in 2019. We had a global team meeting where the future of the record and playback platform was analyzed and discussed. We came up with development guidelines and decided to decouple the original actors. We decided the intake of the data and the saving of the data should not be coupled together. At that point in time, we actually made a decision to move away from the actor framework for a couple of reasons. The people we had working on the original actor framework were more senior LabVIEW developers, but with the number of customers we had with interest in this, we said, wow, we need to bring on some possibly less experienced LabVIEW developers who are maybe even new to object-oriented programming. How can we make this easier? We thought that DQMH would be a little bit easier for them to understand because of its correlation back to the NI-queued message handler. And then the scripting tools that are associated with DQMH made things a little bit easier for us to modify. We actually started with those and made some of our own tools. Then we've since then released an alpha and a beta with different features that kind of correlate. We migrated as much as we could over from our actor framework. We basically had to gut some of the stuff and move it over, but we wanted to make sure we didn't lose any of that initial effort, which we were actually successful in. And this month we've had some of the initial systems being deployed on our, I'm calling it the 2.0 framework. So where are we today? Other than just the coronavirus, we got quite a bit planned for the future with this. We're working on some material, some video, and we're looking for feedback as well as what you guys think we've done good and bad. So feel free to continue the conversation in Discord for this after. Our goals for this whole platform-based approach was to make it for record and playback. We wanted to use DQMH actors for the modules, again, to maintain compatibility with our actor framework logger. And we wanted to have this idea of data flowing through sources, sinks, and processors, which we're going to talk about in detail in a few minutes. We also wanted to make sure that we could have any n number of sources, sinks, or processors be injected at runtime and have them map to each other in different ways. We decided to use classes and dynamic dispatch for plugins, and we were really aiming for very little coupling. The more we could break things up, the better things became. So let's take a look at the architecture. This is kind of the big picture of the framework of everything. So we'd have a client, and in this case, the client might have their own user interface that they've designed. Maybe it's running on robot operating system or something else, a Linux machine. They have something in vehicle that they have already as a UI, and they just want a black box logger from Conrad. And so we've built our own debug UI so we can test things. But the idea is we would send stuff as a data stream, and that's just no command response. It's just our data coming up so they can view stuff live. And then we have things that are requests and broadcasts for them to control the logger. We have this idea of an interface manager. So right now you could use 0MQ as a communication layer through the API, or we could change that out. Actually, in the end, this idea of the interface manager came from our original actor framework logger, because at one point, due to various things, we had to change the control of the logger to GPIB. You don't want to know why, but we had to be able to send commands over GPIB instead of Ethernet or any other bus. And so that was an interesting thing. And luckily, we had this interface manager idea in there, and we were easily able to swap out libraries for how that worked. We also have a standard error manager, system info that tells you about things like system health, processor memory, that type of stuff. Synchronization is key to our whole data logger. Everything's using the PXI clock, and we can trigger off the PXI clock. And so that's kind of monitoring all of that. And we can also synchronize to GPS. The configuration manager is kind of how we set up all these things that I'm going to talk about in a minute, these sources, sinks, and processors. And the DME, this is really the heart of the entire data logger. It's the data mapping engine. So this is the Conrad Technologies data mapping engine. We call it the DME. At the lowest level, there's 3 plugins that can be configured for the data mapping engine. We call them sources, sinks, and processors. And this can be anything that you want. So a source will provide data to the engine. When you're thinking of a data logger, you think of a source usually as just like CAN hardware or a DAC card or something like that. But a source could also be a file if we're looking at this for playback. So a source can be anything. I'm just putting data into the engine. A sink is getting data. It's subscribing. It says, hey, I want some data from the engine. And this is kind of the same. Theoretically thinking, you think, oh, a sink, that must be a file. It can be a file, but it can also be a piece of hardware. We can do output through sinks. And then a processor does both. It's kind of somebody who sits in the middle. So a processor receives data from the engine and provides it back to the engine. It can act as an interrupt. And I'm going to turn it over to Chris now because he's going to walk you through the idea of topics and how we interconnect the sources and sinks.
Thanks, Becky. So I feel this slide does a good job of showing us visually the main entities that the mapping engine deals with. On the left-hand side, we've got sources, or source actors. Sources have methods that are implemented by plugins for specific hardware interfaces, such as CAN-FD, LVDS, or UDP, but also software interfaces, such as TDMS or binary file I/O. These sources read from those individual interfaces and publish data messages to a topic on the message broker. Data sinks can then subscribe to those topics and receive the data messages. So for example, we might have video to binary topic or a CAN to TDMS topic. Just like the sources can be hardware or software, sinks can also be file types or hardware interfaces, allowing captured data to actually be played back. The message broker kind of behaves a little bit like a many-to-many queue. We can have one or more data sources publishing data of a specific type. Any sinks subscribe to receive that topic, or any sinks that are subscribed to receive that topic do so. For example, we might have UDP data published and what's the plural of sunk, and sunk to multiple file types such as TDMS or binary, or even rebroadcast via a network adapter. Processors are kind of where things get really interesting though. A processor can subscribe to a topic and carry out some kind of processing task. For example, data decimation or filtering. In this example, we might be looking for a particular CAN frame. The processor then publishes data to a subtopic which can have its own sinks subscribed to it. Another example might be to have a processor listening for a trigger, discarding data until a trigger is received and then publishing it to a sink. So, source publishes the data to the broker. The processor who's subscribed to that broker receives it, modifies it or filters it in some way, processes it, and then publishes it to any sinks that are registered to receive that subtopic. So a few acronyms, because we've talked about topics, etc. So a module, when we talk about a module, we're referring to an independent DQMH actor, such as the data mapping engine. The data mapping engine itself is a DQMH module. The interface manager is a DQMH module within the larger system. We also have a system info module. That's a DQMH actor that monitors things such as memory usage, CPU usage, etc., system resources. When we refer to the DME, we're referring to the data mapping engine, sources, sinks, processors, and any combination thereof. We can have multiple modules. When we refer to a topic, we're talking about a group of sources, sinks, and processors that are all broadcasting or receiving data of the same type. So we might have a topic that is CAN data being published and being received by a TDMS file. That would be an example of a topic. A mapping is a group of topics. A collection is a group of mappings. So in a typical customer data logger, they might have multiple LVDS sources writing to TDMS files. They might have 6 CAN channels writing to a single TDMS file. They might be monitoring UDP ports for some radar data, for example, and rebroadcasting some of it via Ethernet and filtering and streaming some of it to disk. So a collection is that kind of customer configuration, which is a group of mappings. And as Becky said, our sources, sinks, and processors implement plugins. So the data mapping engine is obviously coded against our parent, source, sink, and processor classes. And then at runtime, we inject the specific class that we want to implement those functions. So let's take a look at the API. So what I've done is I've created a number of demo block diagrams that show the API and actually show this running. So in this very first case, we've got a single UDP source and a single text sink. So we're going to listen for UDP traffic on a port, and any data that we receive, we're going to write that to a text file. So in terms of the API on the block diagram, we can see we create a topic. We've given it a name and we create a topic. We then add a source or a producer of data to that topic. It has a name, it has a configuration, it has a class. We add a sink, and then we can run the source and the sink. We start them separately so that we could perhaps run the data source to make sure that it's actually producing data before we start writing it to disk. We define the configuration of the sources and the sinks as a JSON string, and we pass in a class, which will be the implementation class that we will use. For this example, I've created a simple UDP sender that will broadcast string data to that UDP port that will be then received by our UDP source within our framework. So we can see we've got the same port number there. We've got a text file that's been saved in the folder on the left. Let's go ahead and run that, and let's just broadcast some UDP traffic. We can go ahead and stop, and we can see that a text file has been created. And when we open that text file, it's got a timestamp, a UTC nanosecond timestamp with the UDP traffic that was broadcast. Okay, the next example of this would be where we might want to actually save data to 2 different file types, perhaps for the customer, or even one of the sinks might be retransmission of the data back over Ethernet. In this example, I'm going to just save the single UDP data to 2 distinct text files. So the block diagram looks very simple, very similar, except we've got a second sink being added to the topic with its own JSON configuration. So I'll go ahead and run that quickly. And we can see 2 text files have been created. And when we take a look inside those, we'll see that the same UDP package or UDP packet has been received by both. And we can also see that the timestamp and meta information is the same because it's the same data that was received at the source that's merely being broadcast to both or being received by both of our sinks within our system. Our next example is a typical user case where a customer might want to actually aggregate 2 data sources into a single sink. So an example of this might be that they're receiving UDP traffic from multiple radar devices, but want to actually log that into a single file. So we can see, again, the API, very, very similar, apart from in this case, we've got a second UDP source being added to the topic, again with its own JSON-based configuration, this time just looking at a different UDP port. So effectively we're creating we're spinning up 2 source DQMH actors that are listening on a specific UDP port for traffic, and then are publishing it to the broker. So we go ahead and run that, and we're going to go ahead and alternate our 2 UDP senders, each broadcasting a different message. And we can see that a single text file has been created. When we look at that text file, we'll see the UDP packets have been effectively both written to the same destination. the timestamps as appropriate. So that's kind of a typical use case where they might want to actually aggregate data into a single destination, either for retransmission or into a single log file. And this is personally my favorite example, which is where we've got a single data source. In this case, we're going to listen for that UDP traffic again. We've got a single processor where we're actually going to modify the data or filter the data in some way, process it, if you will, and a single sink. So, actually, in this case, two sinks. So we're going to actually log raw data and process data. The processing that we're going to do here is simply to take the UDP packet string and make it uppercase, convert it to uppercase characters. So we should have one file of process data and one file of raw data. As you can see, the API is a little bit more complex now, or the implementation on the block diagram is a little more complex because we've now got two topics. We've not only got the topic for the original data that was being received by the source and then passed to the broker, we've also got a subtopic. That is the topic containing the process data of which other sinks can then subscribe. We then start the sources, the sinks, and the processors running. You'll also see from the merge error nodes on the block diagram, there is a little bit of sequencing required when dealing with subtopics because it makes sense, right? We don't want to stop certain elements until we've processed all of the data, for example, that's been acquired. So in this example, let's just go ahead and run that. We've got a single UDP string being broadcast, some of it's lowercase. And you can see we've got two text files that have been produced. One of the text files is the raw data that was received from the UDP source, and the second text file is the process data, of which the UDP packet itself, VIWeek, has now become uppercase. As you'll see, the timestamps and the other meta information that was broadcast with the original data packet remains unchanged. So we've only modified the data itself. Okay, so let's take a look at some of the components that we've actually used in there then. So the first one that we're going to look at is the actual messages. So the messages that we send between sources and sinks are objects. Those objects contain a number of elements. They contain the data of interest, the data that we want to send from a source to any number of sinks. They contain some metadata. That might be the timestamp when the data was actually acquired, or T0, the time when the logging session actually began, if we're wanting to look at relative time. They also contain a message ID to uniquely identify the message itself, and a session ID, so that we know which source produced the data, as may have multiple sources running, and also we may stop and start sources individually. So we want to know which logging session those messages were actually produced by. In that example there, we've actually got the data contained within the message. We also support a by reference implementation where the message object contains a DVR, a reference to the data itself. In addition to that, the message ID is replaced by a message GUID, a unique identifier to actually allow us to track the DVR within the system. Let's take a look at those in a little bit more detail. Here we've got an anatomy of a message, the by value implementation. So in order to build our message object, we not only require the data, we actually have to provide the message data, perhaps some formatting information, but also an index so that we know we're receiving contiguous messages, and the metadata itself. In this case, the example I'm showing here is a timestamp. High throughput or small data messages can be sent by value along with message metadata, and that works really quite nicely. For larger messages, though, we want to use a by reference implementation. So the by reference implementation looks very similar. Our message has an ID or a name. Our message has some metadata as well, such as timestamp or T0, but rather than containing the actual data, it contains a reference to the data. messages with large data payloads, such as LVDS, can be sent as by-reference messages using a DVR or even an eDVR if we want a zero-copy implementation, where we're writing directly from hardware to TDMS file, for example. But of course, if we're then publishing data via DVR on the source side, we need to understand when it's safe to actually release that DVR, especially in the case of something like LVDS, where the data packet size can be hundreds of megabytes and we can accumulate gigabytes of memory in just a few seconds. We need to make sure that we're managing those DVRs. So in this diagram, what I've actually shown is how we're actually managing those data value references. So at the time of building each message, the topic knows how many recipients, how many syncs and processors are subscribed to it. We maintain a subscription list, so we know how many recipients of the message there should be. We also change the metadata slightly so that rather than just a number, we've got a GUID. So given that we give the message a unique ID, and we also, as part of the message metadata, store the number of expected recipients for that message. And we do that on a message by message basis, because one of the requirements, as Becky stated earlier on, was to be able to spin up new recipients on the fly, even during a logging session. So we need to know on a message by message basis how many people will expect to receive that message. We also provide the metadata. So that's on the broadcast side. So here we're taking some data, in this case a variant, and the output of that is a message object containing some metadata. The message object only contains a reference to the variant data, not the data itself. On the recipient end, we decode our variant message or our message object, and we pull the DVR out from it. Now, in this particular instance, I'm showing this on a single block diagram, but we've actually moved this to be an asynchronous process. But what we actually do is we decode that message object, we pull out the DVR to allow us to access the data in the recipient, and we also pull out the GUID. That GUID allows us to do an asynchronous check to say, okay, I've now received this message. We know how many expected recipients there are, so therefore we know when it is safe to release the data value reference. So we acknowledge the receipt of each message in the receiver or in the sync or the processor, and if it has been received by all of its expected recipients, the reference can be released. As I say, I'm showing that on a single block diagram, but that's now moved to be an asynchronous management process where we periodically look at have all messages been received, or which messages have been received by all recipients, and then release the DVR. That also allows us, in the case of the eDVR, to know it's been received by everybody who needs it. You can now release the bytes and how many bytes to release on the source side. So all of our interface developers, our hardware, our file I/O developers, as Becky said, we put a large team together to actually assemble this data logging project, and all of our interface developers need message types for the data that they wish to send, broadcast from a source to the message broker, and receive. If they're writing syncs and they want to subscribe to some data, they need to know how to decode the data that they're receiving. So we provided by reference message types as palletized items, and also, by value object types as palletized items, but also by reference messages. However, the malleable VIs provided a mechanism for having a single build message, decode message that adapts to the data type that's wired to the connector pin. So we can have a single build message that takes in whatever data type we want and adapts to that. In addition to that, the type specialization structure allows the passing of a class whose private data or accesses differ, or classes who are unrelated. In this case, syncs and processors. They have somewhat different private data and different methods to act upon that private data. The type specialization structure allows us to pass either a sync class or a processor class into that VI, and it adapts as need be. Which brings me on to the second slide, which is seeing broken wires on block diagrams where the run arrow is not broken still freaks me out, and I've been using malleable VIs now for quite some time, but I not got used to that at all. Okay, so in addition, messages under the hood. So we use maps to keep track of the message indices. So I talked about we have an index for all of our by value message types so that we can ensure that we're not missing messages and they're arriving in the correct order. We're talking about a data logger that is taking data from a source to a sink at several gigabytes per second and writing to disk. Customers want to know that messages are not being missed. So one of the things we did was to put a message index in there so that we would know if there were non-contiguous messages. By using a map, we were able to very conveniently build a key value lookup table, if you will, to allow us to track message indices across several mapping sessions, across several topics, to ensure that data was being was received and nothing was being missed. Okay, so I showed you some block diagrams with some APIs on there, but obviously we're not going to ask our customers to program with an API on the palette. So what we needed now was something to take that API for the creation of topics, sources, and sinks and be able to spin them up on the fly. So this shows our data mapping engine, which effectively takes a file containing mappings. You'll see them in a second. So this is the data mapping engine module, and it allows us to take a file containing JSON strings that describe various mapping combinations of sources, sinks, processes, etc., and to turn that into a runtime configuration. So in this case, I'm going to load a mapping similar to what we had previously with a single source, a processor, and 2 sinks. The mapping engine also allows us to broadcast certain state information about the condition of a particular module within that runtime configuration. So we can see we've got our JSON-based string, our JSON configuration there. We're now going to instantiate that and to bring all of the various sources and sinks into memory, inject their required types. We can see what actors have been created as part of that configuration and what their status is. In this case, they're idle, and we have 2 topics. We have a UDP topic and we have a processed data topic. So let's go ahead and run that mapping now. So we can run that and we can see that the logging status has changed. Each of our topics now has a logging status, and we can go ahead and put a message in our simple UDP sender. Let's put something in there. And let's go ahead and send some data. Let's send a lot this time. Let's not just click the run button. Let's hit run continuously on some UDP traffic. Go ahead and stop that, stop the recording, tear down all of the topics in the correct order, in the correct sequence, and let's take a look at the file output. So we have 2 text files similar to the previous example. Let's take a look in those. So we've got a processed and a raw data. We've got a lot of data in there this time, and we can see that we've got raw data, raw UDP strings, and then we've got our processed data where we've taken everything and converted it to uppercase characters. So as Becky mentioned, the mapping engine is just one part of a larger project where there are multiple actors, multiple components, all of them DQMH actors, but the mapping engine is the part where we're basically spinning up multiple n number of sources and sinks and combinations, and then allowing them to subscribe and receive data as per a customer configuration of which we have no knowledge in advance of what that might be. Becky, do you have anything else that you want to add at this point?
No, I wanted to point out, though, anyone who's used DQMH should have slightly recognized that last front panel that Chris showed. So that DMEC itself is actually a DQMH module, and that kind of is a little bit modified stuff we added, but it's the tester VI, realistically. So if there's any questions, I'm going to go ahead and check and scroll, Chris.
Yeah, so that was one of the key things about working with a team with differing levels of experience and differing roles within the project was give me a DQMH tester to allow me to test your API, and we could all work with confidence without really knowing too much about what each other was doing, provided we distributed an API tester with each of our modules. So in this instance, I create the DME, but my internal customer, if you will, he installs a package, he runs the API tester, he checks out, okay, what requests can I make on the DME? Load a configuration, for example, and he can subscribe to some broadcasts such as configuration loaded okay, module started running, etc. So it also makes for a really nice demo as well, for being able to just show the thing up and running without all of the additional, the user interface, the 0MQ stuff, the system monitor that we also have as part of the system.
And so basically, I mean, a lot of the control through the API, a lot of it will go through the core. And so those same commands that Chris was literally pushing buttons for are the commands that come in from the customer's UI. So it's kind of an interesting thing. I'm scrolling through quickly. I'll post some links for some of the other stuff. There's a good question. I don't know if I know the answer to it, Chris. Does it mean the DVR is sent through the broker and accessed by the processor and syncs, which I believe is yes. And then can the processor and syncs be another computer than the source?
Yes, absolutely. Yeah. So there are multiple transports. In the case of the DVR, I'd have to seriously give that some thought, but in the case of the broker, at the minute, the broker types that we support, we have a TCP/IP, we have an event, a queue. I've only tested those out with the VIWeek implementations. I missed that question, Becky. I'm not sure where that was.
That one was over in.
Yeah. Okay, some good information by Darren, just basically stating that the stability, perhaps of maps and sets, and also malleable VIs is improved in 2020. So that's good to know.
I don't think we ran into any major issues that I know of.
We've had some strange non-relinking to dependencies within the malleable VI.
But nothing that broke our code or stopped us.
How would we know? It's got broken wires in there anyway.
The one thing we haven't tried, I know, is we haven't tried running it on real time. It's not to say it wouldn't run. We just haven't tried it. One of the reasons why is some of the hardware we're using doesn't have real-time drivers. So, because I know that question typically comes up too.
A good question there about using the DVR rather than the by value, but saying that they don't have that much data. I think that there's a real balancing act that you need to look at, which is not only the size of the data, but also the frequency of the messages that are coming through. We've definitely we kind of did a wholesale switch to a by reference implementation, and actually took a hit on some of the smaller, more frequent data packets. So that's why we actually support both by reference and by value messaging through the broker.
And I think the real reason, and the whole reason for the DVR, was to do zero copy. That was part of it. And a lot of it's those serial deserialized cameras. They have a lot of data. You've got huge resolution cameras coming in at up to 60 frames per second. And so, like, one of the cameras we've worked with actually gives you a low res and high res image, and we have to separate streams. So there's a bunch going on with those cameras. There's a lot of work and a lot of configuration that has to happen.
And that's a pretty scary combination, actually. I know that's one of your guys, Becky, working on that, and he's actually had to implement two sources talking to the camera to pull out the various components of the image, the different resolutions, and then have a processor actually work out, okay, which packets can I discard to almost like stitch that information back together.
And it was nice that we got to the point, the framework was far enough along when he got to that point that he could actually use it and figure out a way to make it happen. And the other nice thing, and it wasn't really shown in here, like we talked about briefly the inheritance and having the children. But one of the things that we've really relied on with our sync source and processors are we could have a more generic parent and then have multiple children going down to like grandchildren and great-grandchildren that only override certain methods that are necessary, because a lot of them may share the same method. Like let's say XNet, we want frames or channels or different things. You might have the same open to the hardware, but you might change how you're configuring the channels versus and all of that stuff can be, but you don't have to have separate instances. You can override what's needed. And I know that helped a lot with the Conrad device driver as well.
Okay, got a question. How do we generate? So we've got a custom function that we wrote to generate the timestamp as per the customer requirement. I can't remember exactly. Was it nanosecond, Becky? I want to say it was.
Yes. No, it's the Unix timestamp. Is that what you're talking about?
Yeah.
Yeah. There's a special VI that's using a call, and that was I believe Sasha wrote that, didn't he?
Yeah.
And it was so we had universal.
Maybe Thomas.
Oh yeah, it might have been Thomas. Yeah, it's one of the two. They it's interesting because this is my real first large cross-continent job. We've got people working in Germany, the UK, the US, and it's so many people, so many time zones that even sometimes we get confused. So it's actually kind of interesting because we will remote into computers in Germany or the loggers to do testing. And obviously the timestamps don't match. So having that Unix timestamp was kind of a nice addition. Yeah, and the DVRs really are meant for a lot of data.
Yeah, I mean, the LVDS in particular, those packet sizes are huge and fast. It's not a good combination.
There's a question, how is the DVR unflattened on the destination PC?
Yeah, so you saw there were two malleable VIs in the project. So the second malleable VI is the decode, and yes, we have to provide an expected data type. So which kind of makes sense, right? Because our sources and sinks, there are certain permutations that make sense and some permutations that don't make sense. So our data is either U8 array or string, or it's something custom like a CAN frame coming from a Gopal card or something like that. So our decode VI, it's a malleable VI, but one of its inputs that it adapts to is expected data type. Yeah, really good comment from Fabiola about memory profiler. That came in extremely useful. Becky, do you know the camera for the current customer? What's the data size? I think you've got something in this. Becky's looking for something.
Can you guys see this?
Yep, so there's image processing.
Yep, I was muted, so I was talking the whole time. But images obviously are just pixels, and it's a bunch of zeros and ones, and all of these come from an image sensor. And there's a standard out there from MIPI. It's a mobile standards board called CSI2, And there's different serializer chipsets. And basically you have to have a matching serializer and deserializer. And then there's a layer in between that typically is FPD link or GMSL. There's GMSL1, GMSL2, GMSL3. GMSL2 is probably the most popular. But what we're talking about here is we have custom Conrad hardware that actually does this part. We pretend we're like an ECU. So a camera module from a supplier will have an image sensor and a serializer in it. And we physically have a cable coming into us. And this is custom Conrad hardware that is basically emulating an ECU. I think if I go to the next one, that is deserializing it, takes it into a Flex Rio and so forth. So it's a special card that Conrad makes that does this. And so that card, because it's a Flex Rio, can be synchronized to PXI. So you can have truly synchronous video and other data. Now, these cameras are not fun to deal with. You have to basically know how to program them or set them up via the registers. There's a bunch of fun stuff. So you better find someone who's working with the camera that knows how to do it and configure it. And there's hours of work into that. But this is large amounts of data. Some of these cameras are like 8 megapixel, 60 frames per second. Some aren't. And then the camera module itself, before it serializes it, might do some processing and send other stuff with it, as well as beyond just the serializer. You might have an Ethernet port or CAN coming out as well with it.
Becky, I think we had a question just about the decoding of the DVR just quickly before we wrap up. Could you go back a couple of slides just to the one where we talk about really the management of the DVR? There we go, that one. One more. Yeah, so this might be an example inside the malleable VI where we've got an expected data type coming in. Oh no, that's a building. It's the one with the in-place element structure. Next slide.
This one, right?
There we go. Yeah. Okay, so we got a message coming in. We'll pull the DVR out, and this is effectively inside a malleable VI that is adapting to the output. In this case, it's taking a variant as the output. As I mentioned, the message acknowledgement now happens asynchronously to improve performance.
Looks like we went over a little bit. I don't know if there's any other questions. We can obviously keep the conversation still going in the Discord channel. Otherwise, I want to thank everyone for coming. Is there anything else you need to add, Chris? The video it is recording and it will be alive or available after the session. I think we're going to have our own page on the LabVIEW wiki. I was having some problems getting on there earlier today. I don't know if there's been a lot of traffic. I'm going to work with Q to get that on there. In the meantime, if you want to rewatch everything we went to or slow it down at any point, you can use the same link. So as soon as we take this live meeting offline, what'll happen is that same link should take you to the video. I don't know how long it takes to process, but that exact same link you used to get in here today should let you watch the video. All right, thanks everyone.